Hello and welcome students. This is Akshay and you are watching your favorite channel Alpha and Omega, and in today's lesson we are going to learn vector geometry and its importance in a basic geometry. How we can use the vector analysis in a basic geometry. Okay. So without any delay, let's start finding out about the beauty of the vectors in a physics as well as in mathematics. Okay. So basically the vector geometry, in the vector geometry, we will learn that how the vector is useful in the geometry to prove some basic things, right? Like two lines, if two lines are parallel, if two lines are perpendicular, we can prove those things by the help of vectors. And we will also know that how do we evaluate some magnitudes of the resultant vectors. How do we evaluate the direction and the bearing of any resultant vector very easily? Okay. So without any delay, let's start. And in today's lesson, we are going to learn about some basic things like what is the vector. Okay, so basically, if you are looking for the definition of the vector, then it is very simple. Any quantity which always needs some sort of a direction. Okay, which always needs any direction to specify itself is known as a vector. Okay, and a quantity which does not need any quantity, which does not need any kind of direction to specify itself, to define itself, then these kind of quantities are known as a scalar quantity. So the first thing that you need to remember, that what is the quantity? So quantities is anything, okay, which may or may not be physical. Okay, quantity may be anything. It may be physical or it may be non-physical. Okay, like the temperature, right? The temperature is a physical quantity, okay, which can be measured, okay. But some of the quantities which cannot be measured, those are not physical, okay, like my feelings, like my sadness, like my happiness. So happiness it cannot be measured, right? So it is not a physical quantity, all right. But sometimes you say that I'm so happy today, okay, but you cannot quantize it, okay. Anyway, so as you know that if I say that what is the difference between the speed and velocity, then you must have studied this in the physics, that the speed is basically same as a velocity, but the velocity is itself a speed with a direction. Okay, so we can say that velocity is a speed combined with a direction. Okay, so basically velocity is a vector quantity and a speed is a scalar quantity. Okay, let's move ahead and let's find out what are the vectors. Okay, so as we discussed earlier that there are two types of quantities. Okay, so basically quantities are two types, right? So if we start with the quantities. Okay, so basically quantities are two types, right? So if I make a flow chart, then we can clearly see that one quantity is known as a scalar quantity, and the second quantity, it is basically known as a vector quantity. Okay, so quantities, there are many kind of quantities exist in nature. Some of them are physical, some of them are non-physical. Physical quantities are only those quantities which can be measured, right? Like a temperature, right? Like a electricity, right? Like a mass, like a length, all those are physical quantities, alright? So in those physical quantities, some of the quantities are a scalar and some of the quantities are a vector quantity. So scalar quantities are the quantities which does not require any kind of direction. They contains only a scale, right? Only a magnitude. That is why they are known as the scalar quantities, alright? Like if I say my mass, right? My mass. So mass, if I say it is 2 kg, right? So it does not need any direction to specify that in which direction it is existing, right? So mass is a mass. So in a mass, you need not to tell any kind of direction, like a temperature, right? So in the temperature, you does not need to define its direction, right? So temperature also does not require any direction. Like if you say right now the room temperature is at 27 degrees Celsius, or you may say 60 Fahrenheit. So you won't say that in which direction the temperature is the 27 degrees Celsius, because it does not need any direction to specify itself, right? So in that manner, we can clearly say that the mass, temperature, right, the time, right? If I say it's been 2 hours, I'm taking this class. It's been 5 hours I'm studying, right? So if I say it's been 5 hours since I'm studying, then it does not require any kind of direction, right? You won't asking somebody that in which direction it's been 5 hours, right? So in that manner, we can say that the scalar quantities are the quantities which does only possess a scale or any kind of a magnitude, so it does not require any kind of a direction to specify or define itself. That is why these are known as a scalar quantity. On the other hand, a vector quantity is a quantity which basically always needs some sort of a direction to define itself. Like what? Like recently we took an example of the velocity, right? So velocity itself, a vector quantity. If I say that a arrow or a rocket, basically if we say a rocket is flying at the velocity of 500 meter per second, then you should specify the direction, in which direction it is flying, right? In which direction it is heading, right? So here the velocity itself a vector quantity, like acceleration, right? So in the acceleration is also a vector quantity. Okay, it also requires a direction to specify itself, to define itself, that in which direction the object is accelerating or decelerating, okay, or you can say retardation. All right, so you must also think about that, is there any kind of other quantity which is existing around us, which is neither scalar nor vector? So you're right, you're asking correct question in your mind, that there are third quantity also existing in the nature, which is called tensor quantity. Yes, you heard it right? So third quantity, if I say the third quantity, so the third quantity is basically tensor quantity. Okay, so tensor quantity is you may say that it's a kind of a vector, right? It's a kind of a vector, but its direction is not specified, right? Like if I say pressure, all right. So if I take an example of a pressure, so in the pressure, you must know that if I draw a box here, okay, let's say this is in a container, okay, this is a gas chamber, all right, and in this gas chamber there is huge amount of gases filled in that, okay. So if I closely observe that all the gas particles present in this, they are all moving in the different directions, right? They are putting pressure on the container's wall, okay, from inside to outside, right? So the pressure is from inside to outside, right? Here. So I can say that the pressure inside, here the particles are putting pressure in this direction, here the particles are putting pressure in this direction, here the particles are putting pressure on this direction. So pressure is all in all the direction. All right. There is no finite direction. There is no certain direction of the pressure in which it is exerting. All right. Although pressure is a direction, because pressure is a vector quantity, right? Pressure, if I say is in a finite direction, yeah, because the pressure is equals to force divided by area, right? So force is a direction. In that manner, we can say that the force is a direction. So force per unit area is a pressure. All right. So we can clearly see that the force is a vector quantity, but its outcome with the area is a pressure, and pressure is a tensor quantity. But since it has a no certain direction, let's take another example. If we have a bucket of a 20 liter of water, okay, then the whole water is applying pressure on a different directions. All right. So that pressure, created by the water on the container's wall is in all directions. Okay, it is not in a single direction. Okay, so pressure is there, but it does not have a single direction. Okay, and in the vector quantity, it is compulsory that you should specify a quantity which you should specify a quantity as a vector which has only single and only single direction. Okay, it does not, if it is not having a single direction, that means it is not a vector quantity. Okay, so the quantity which is a multiple directions, okay, to operate itself are known as a tensor quantity. So one of the example I gave you here, the pressure is a quantity which is known as a tensor quantity. So basically, there are some multiple quantities. Okay, so scalar quantities which have only scales, like a magnitude only, which does not need any directions to specify itself, are called scalar quantities. And on the other hand, the vector quantities are the quantities which are always having a magnitude, that means a scale, as well as direction, okay, and which always needs a certain direction, a single direction to define itself, are known as a vector quantity. And those quantities which have a direction but not a specified or defined direction it has, Such quantities are called what? Tensor quantities. Okay, it has a direction, but the direction is many direction. Okay, not a single direction, but at a point of a time, if you see only a free point, only this, then you will see the pressure in this direction. If you see on this place, if you see the pressure, this is in this direction. But if you see the whole system, the pressure is in many directions. Okay, so it's a simple thing to understand. Okay, so there are three type of quantities existing: scalar quantities, vector quantities, and a tensor quantity. Okay, let's move ahead, and now we will go through the vector quantities more specifically. Okay, so what are the vectors? So as we discussed, the scalar quantity is a simple anything in life that can be described as just as a number. Okay, if I say 5 kg, okay, if I say 5 kg, right, 5 kg is a mass, right? It does not need any direction to specify itself. So 5 is a number and kg is its unit, right? So 5 kg becoming a quantity, and this quantity is a scalar quantity. Okay, so scalar as only scale, right? So scalar quantity is a simply anything in life that can be described by just a number. All right? Okay. Now let's move ahead. Example: the temperature. Example: my age. Okay, if you say your age is 18-year-old, if you say your age is a 15-year-old, that means it does not need any direction, right? Nobody will ask you that in which direction you are going. All right. So the temperature, the age, all these things are scalar because they always need a number to define themselves. Okay, they don't need any kind of direction. All right. Okay, let's move ahead. However, a vector quantity is a quantity that needs direction as well for it to make sense. Okay, without direction, the vector quantity does not make any sense. Okay, let's move ahead. Vector have both magnitude, that means the size, that is the scale, and its direction, right? If you does not have a magnitude and only direction, right? If you does not have magnitude and only direction, that means it is a zero vector, right? Because without magnitude, it's a zero. If the magnitude is zero, right? Magnitude is zero, that's a zero vector, right? But it has a direction, that means it's a zero vector. Okay, so both quantities should be there. Okay, magnitude as well as the direction. Okay, let's move ahead. Example: velocity, right? Because it is speed and direction, right? Speed and direction, right? Example: wind velocity is 20 km/h in east, right? So that means it is moving from west to east. All right, so it is the direction. Okay, displacement, distance plus direction. Okay, with the distance, if you need to specify the direction of the distance or length, it becomes what? A vector quantity. Okay, let's move ahead. Example: displacement of a Leeds from York is 25 miles west. Okay, so that means it is in the west direction from Leeds of York from the Leeds. Okay, it's basically 25 miles in the west, right? So basically it is also a vector quantity. So displacement is also a vector quantity, and velocity is also a vector quantity. Okay, let's move ahead. Now velocity are the directed quantities. Okay, so final conclusion is that the velocities are the what? Directed quantities. They always need some sort of a direction or any specific single direction to make them sense or to define them. Okay, let's move ahead. Okay, so how do we represent a vector quantity? Okay, now this is the question rises, that how do we represent any vector quantities in a calculation or in any kind of operation, mathematical operation? How can you define it? Okay, so simply a vector quantity can be defined. Initially, there's been many challenges in the scientific community. How do we represent it? Okay, because we come across a lot of calculation, we come across a lot of writings in a physics and mathematics books, but they never knew that how to define it, right? So to define it, basically initially they thought that we will represent it by a capital letter. All right, the scientific community thought that we will represent a vector quantity by a capital letter only. Okay, so if you represent it by a capital letter, it won't make sense, because in sentence many times a capital letter comes, right? So automatically you need to consider all the capital letters vector quantity. That means it will make no sense, right? So that plan already got failed. Okay, so this was failed. Okay, it didn't work. Okay, after some time they thought that we will represent a vector quantity by a small letter. Okay, but small letter also comes in a in any sentence multiple times. So that also didn't work. Okay, it also hold, or it's also failed. Okay, so later on they come to a conclusion that what if we represent a vector by any capital or small letter. Okay, but just simply you need to put what, an arrow on it. Okay, if I make an A and if I want to represent it as a vector, you just need to put an arrow on it. Okay, if I represent a B here and I want to represent this B as a vector, that means you just need to put an arrow on it. Okay, and this arrow, it does not mean that you are going from left to right. Okay, you need not to get confused that this B, it has only this direction. It has nothing to do with the direction. Okay, it's just showing that it is a vector. Okay, its direction is a different matter. Okay, so if you say that if you want to represent the vector in this direction, should I place it like this? No, it is not like this. You need to represent always like this only. Okay, the direction of any vector, we will evaluate that direction of that vector separately. Okay, it is a separate matter. Okay, so it's been concluded that we will represent any vector in an algebraic form simply putting an arrow on it. Okay, so basically the vector representation was quite a challenge initially, but later on they solved it. Okay, just by putting an arrow on it. Okay, so here this is representing what, a vector. Okay, let's move ahead. Now, if I talk about the representation of the vector, the representation of the vector is basically two types. Okay, so first representation is basically graphical representation. Okay, graphical representation. Okay, and the second representation is basically algebraic representation. Okay, so there are two types of representation. So algebraic representation we had already discussed, right? To represent any vector quantity in form of algebraic format. Okay, so if I put here A and if I put an arrow on it, that means it is a vector. Okay, now how to represent a vector's magnitude and a direction? So it's very simple. Okay, if you equal it, okay, and you want to represent its magnitude, that means its magnitude is represented by the modulus of a vector. Okay, the modulus of the a vector is represented like this. Okay, so this is the modulus of it. Okay, and how about its direction? So its direction is represented by a cap. Alright, so the direction of this vector is represented by a cap. Okay, so this cap is basically denoting the direction of this a vector. So now the question should coming up in your mind, that does it representing the upward direction? No, it's not. It's not representing the upward direction. It's just representing the direction of A. Okay. So what is the direction of A? So the direction of the A, if you want to show it, that at that time you will need what? Graphical representation. As I told you, this is only a graphical algebraic representation. So in the algebraic representation, you cannot show everything in the algebra. All right. So here the direction can be shown as a graphical representation. So if I say I want to represent a vector, right, graphically. So how do I represent? So basically you need to draw a line. Okay, in this line, the length of the line, right? If I mark this point as a A, and if I mark this point as a B, then I can say that from A to B it is an AB vector. Okay, so it is AB vector. Alright, from A to B it is AB vector. From A to B its length, basically it is its length. Okay, from A to B there is a length. Okay, and this arrow is representing the direction. Okay, now you can say that it is left to right. Alright, so it is left to right is the direction. Alright, or you can say west to east. Alright, so west to east it is the direction of the AB vector. Is shown here. Okay, if I say that the length from A to B is 20 centimeter, then I will say that the 20 centimeter is the magnitude, and from west to east, or I can say that from left to right is the direction of this AB vector. So it's quite simple, right? But algebraically, what you will say that the direction of the AB vector in this direction is A cap, Okay, so basically, if this is a vector, capital small a vector, okay, if I say that this is a small a vector, that means its direction is this direction is basically a cap, okay, and the magnitude of this a vector's magnitude is basically what, 20, what, from a to b. Okay, I hope you understood the concept of representation of any vector. Okay, so this is basically algebraic representation, and this is what, the graphical representation. Okay, in the graphical representation, you basically have an independence. Okay, you have some liberty. Okay, what's that liberty? You can move this vector from one place to another place very easily. Okay, you are not hindered by anything. All right, you can move this AB vector from one place to another place very easily. Okay, how can I do that? Okay, let me show you. So if I say I have a vector quantity like this, okay, and it has this direction, okay, sorry, yeah, and it has this direction, okay, and this is from A to B. All right, this is AB vector, okay, this is AB vector, or you can say that a small a vector. Okay, so here this is AB vector, is a small a vector, okay, and in this AB vector I can say that its direction is left to right, okay, and the length of AB is basically its magnitude. All right, if I make another line, this is a line, all right, okay, and in this line, if I say that this is the same direction, okay, the same magnitude from A to B, the same length it has, the same direction it has, that means it is also equals to A vector. So two vectors are equal, okay, two vectors are equal if the direction and the magnitude, that means its scale, are equal to each other. Okay, so in that manner we are very precise and we are very accurate that if you want to move this vector from here, you can wipe it out and we can build it, we can make it somewhere else, okay, because it will be equal to this one, right? So it's giving us a liberty. All right, so in this liberty we can clearly say that we can move one vector from one place to another place very easily. Okay, if I say that this is a vector in the upward direction, okay, and this is CD vector, okay, from C to D, okay, and in the CD vector the direction is downward to upward, and I make another line here, it's also it's downward to upward, okay, they have same magnitude, okay, and they have same direction, that means this is also CD vector, okay, they both are CD vector, so that means I can draw this vector, I can write this out and I can make it here. Okay, so it's simple that a vector in the graphical representation, I can move a vector from one place to another place by making a similar type of a diagram. Okay, same type of a diagram, not similar, to be very accurate, a same and equal type of diagram you should make it. That means you will move one vector from one place to another place. Okay, let's move ahead. Now let us know that what are the other terms in the graphical representation of any vector. Okay, so now let us know that. So if I draw a line here, okay, and let me represent this line as a, sorry, it should be straighter one, okay, and in this line, if I say this is a vector, okay, then in this representation you must know that this is basically known as head of vector. Okay, and this portion is basically called tail of vector. Okay, yeah, so you're totally correct in terms of defining it. This is called the head of the vector and this is called the tail of the vector. Okay, so basically this is a full graphically represented a vector, and this is a vector. Okay, if it is the a vector, that means from here to here, this is the magnitude, this is the direction, and this is the a vector. It's quite simple, right? Okay, so this is how we learn a representation of vector. Later on, there is some sort of other representation came in front of us. Okay, in the scientific community, they also thought that why don't we make any letter bold, right? So if I make any letter bold, it can also be represented as a vector. So it also worked very nicely. Okay, and some of the scientists also represented vector in terms of like this is a vector and then putting a line under it. Okay, So if you have a vector, A, and if you want to represent a vector A, that means you need to put a line under it. Okay. So the underline under any algebraic letter also represent what? A vector quantity. Okay. So these are three multiple type of representation we learned. Okay. So let's move ahead. So now vectors can be represented as straight lines, right? As we discussed, this is a graphical representation. Okay. So directed line segment. Okay. In that segment, the line should be directed. That means it has a head. That means which is showing its direction, and it should have a tail, right? Okay. So for example, this is a vector. All right. You can put an arrow here or in the mid of it to show its direction. All right. If you put here the arrow here, it's also representing the same information. All right. Okay. Now this is the direction. This arrow is representing what? Direction, as we discussed earlier. Okay. And the length of this line is basically representing its size. All right. So now there is another representation of the vector which is known as a column vector. Okay. The column vector is a kind of a representation in which we can draw a vector line or vector in a graph, and we need to count the columns. All right. We need to count the columns horizontally first, and then we need to count the columns vertically, right? And we can represent any vector in the format of like 5, 3. All right. So this is also a kind of a representation of a vector. Okay. We need to represent the vector in the column view. Okay. So this is a column vector. Okay. So I hope you understand. So you can see that this is a big large brackets. Okay. And in this vector, these are the 3 columns and 1 columns vertical. Okay. So 3 columns horizontal and 1 columns vertical. Okay. How do we count the columns? Simply draw a vector line, right? This is a vector line. You need to draw this line in a graph paper. Okay. And you need to count the horizontal columns first, and then the vertical column second time. Okay. Let's move ahead. Okay. So like this one, this line is representing horizontally 3, and this line is representing vertically 1. Okay. Okay. And this is basically a vector that we were talking about. Its magnitude is this and direction is this. All right. So vectors are pathways. Yeah. This is also a quite accurate word, that vectors are a pathway. Okay. Let's move ahead. Now I'm showing you here basically a graph paper, a tracing paper, okay, in which each box is representing a specific quantity, okay, a unit value. Okay, if I start from here, if I mark it like if I mark it here A, okay, and if I mark it here B, okay, then I can say that from A to B, okay, from A to B, how many columns are there? So 1, 2, 3, 4, 5. So 5 columns it's covering, 1, 2, 3, 4, 5. And how many vertical columns it's covering? 1, 2, 3. So I will write AB vector basically is equals to U is equals to the magnitude is what? The column, the 5 and 3. So basically this is known as a column representation of any vector. Okay. So here similarly, if I take this example of this, right? So here I can say I can count up like how many columns it's covering? 1, 2, 3, 4, right? I can say that 5, right? If I say 1, 2, 3, 4, 5 columns and 1 column only vertically, then I will write the horizontal columns first, right? So basically it's a 5, okay, and then 1, right? And 1 in the negative direction. If it is upward is a positive, then the downward is a negative, right? So I will represent it as a -1, okay? So 5 -1, okay? So if and I need to mark it as a C and D. Okay, so it became quite simple to know you, to let you know that what is the concept of the column representation of any vector. Okay, so column representation is not a big deal. Okay, you need to just represent any graphical vector in a graph paper and count the number of boxes on the horizontal scale, and then count the number of the boxes on the vertical scale, and at the bingo. Okay, let's move ahead. And how do they look like? What do they look like? So basically, the most common notation for vector is threefold. Okay, as we already discussed, that this is the AB vector. It is basically known as the AB vector. Okay, you can make it more bold, or you can represent any vector and make it in a line, right? So this is also the vector representation. All right. I hope you understand. I hope you understood the basic concept, how to represent the vector and what is the definition of the vector. What are types of vector? We already discussed everything. All right. Okay. Now, Now we will discuss the position vectors. Okay, but I hope that it's been a total, the time is completed. So I hope that you have learned the whole concept of the vector, the types of the vector, and all other things related to vectors. Okay, now next thing coming up is the type of vector. Okay, that thing we will discuss in the next chapter. So up to this time, I hope that you have learned the concept of the vectors very easily, very frequently, and you are making the efficient notes as well. Okay, so thank you so much for being here. This is for today. Let's see each other in the next lesson. Thank you so much for being here. Thank you so much. Thank you.